waiting for the discussion of the. Okay, so let's start thanking again the organizer for putting all this conference together, these two or three communities, maybe four. So what I'm speaking today is maybe some old results, but I think we have never present these results with Braina and Bernard some years ago, and also some new discussion with Sebastián Donoso and Felipe Hernandez, who is a master student in Santiago. So recurrence and nil system, maybe I'm not very original. I wanted to put the titles in the title, the names, of the conference. There will be some nil systems and maybe some recurrence. So yeah. So just this slide will go very fast, but essentially, so we know from this conference too, that recurrence is something that is really related to the combinatoric, the established kind of the relation between combinatorics and ergodic theory. Recurrence is one of the objects that make this link works. Of course, not the unique one. So van der Waarden theorem is one example. And in fact, when you study recurrence and study such many combinatorics problem, you go very deep into the restriction of that a recurrent set presents. So essentially putting recurrence in the middle of ergodic theory and combinatorics is a very natural thing. And of course, as we have seen in this conference from the first day, nil system may play some role. Yes, okay, so let's recall some definitions. John gave all of those yesterday, but I will repeat anyway. I will be working all the time in the topological setting, so I will take compact metric spaces and a homeomorphism acting on it. Yes, I will start with action of the integers. Many times will be minimal, but in fact, you don't need all the definitions to be minimal. Yes, it's classical. For me, it's better, it's simpler, but in fact, it's not necessary to have minimal systems in all those definitions. In any case, I will consider to have minimal systems, so systems where all orbits are dense. So I will consider two types of set of recurrence. So simple recurrence, topological recurrence. Yes, I put just yesterday this to make the difference with John. It's not measured theoretical recurrence, what I'm considering today. So it's a subset of the integers or the positive integers where for any minimal system, you have some recurrence on this set for any open set. Yes? And you can go further, just following the multi-recurrence ideas, and you can define for any S a multi-recurrence set of, or S recurrence, a set where you can multi-recur on any open set of any minimal system in this particular way. Yes. Of course, when you are recurrent for all the S, we say that this set is multiple recurrent. There are many sets. I think that some were discussed yesterday by John, but essentially if you have an infinite set, subset of the integer, the different set is a set of recurrence. In multiple recurrence categories, you have many types of sets that has this property. There are also some interesting examples where you have one recurrence and not two recurrence. So in fact, those categories are different. And in fact, in this paper by Nikos, Emmanuel, and Mate, there is special examples where you are S recurrent, not S+1 recurrent. So you have many examples. I'm not listing all the examples that exist, but I want to mention this very nice result that I like because maybe I work in topological dynamics of Ye, Wang, and Song, where they produce using generalized regionally proximal relation many ways to produce recurrent sets. Yes. So in particular, when you consider some nil system, I'll show at the end, in particular, a affine nil system, you have very concrete way to create recurrence. Yes, just following this regionally proximal relation. So you have many examples of what I said before, but I want to be more restricted. The question today has to do, just because I want to mention, was mentioned yesterday, Kuznetsov question or conjecture, or I don't know. You can ask the same question for restricted families of systems. So for example, you can consider rotations, of course, on compact abelian groups. You can consider distal system, nil system of some order, some family of system, and ask the same question. Yes, do a set, subset of integers, is recurrent, topological recurrent for system in such family of topological dynamical systems in this case. Yes, you will have, so you will have the single recurrence for a family, and you have the S recurrence for the same family. Yeah, so in particular, what is quite classical is to consider the class of minimal translation compact abelian groups, and you recover what is called the Ball recurrence sets. So essentially, this is a way to write them. So essentially, it's a set where you have nice recurrent on, say, by rotations on the torus. Yes, but this is not all what we can do. We have more families of sets where we can try to discover which are the recurrent sets. So this is the very studied, celebrated. I didn't know how to put this, but I think very considered, very question is by Kuznetsov, my baby, no, not by him, that just to know if these Ball recurrent sets are of general recurrence. All this in the topological setting in my case. Yes. So I will skip one slide, we'll come back. So essentially, which is a strategy, or a possible strategy, naive strategy to try to solve this question. Sometimes the strategy I will say here, maybe it's not naive. In many problems in topological dynamics, this strategy works, and essentially consists in, if you have a topological dynamical system, you have what is called a PI tower associated to it, and you can try to prove that starting, for example, in a rotational compact abelian group, this one is the Kronecker factor, topological Kronecker factor. You can try to move up by transfinite inductions of some kind of type of extensions to arrive to this system here, and after project the property of recurrence. I will be more clear. Suppose we know here the recurrence is true because it's a Bohr set. We can try to prove that recurrence for both Bohr sets can be lifted by proximal extensions, for example. This can be a naive strategy, and can be lifted by equicontinuous extension and also weakly mixing extension. I will not define them, not all of them. If you can do this, in fact, you prove the Kuznetsov conjecture. Yes? But this is maybe too naive. In many problems in topological dynamics, this works. In many problems, it does not. Yes? So you can test this strategy, and what is possible to prove is that for proximal extensions, the S recurrence sets lift. Yes, so this is, let's say, it's not easy, but it's classical. You can lift recurrence, S recurrence, and single recurrence by proximal extensions. But what is complicated to lift are equicontinuous and group actions or distal extension. Yeah, this is maybe the main obstruction to this strategy, and there is a very nice progress by Glasscock, Giannis, Butzo, Giannis, and Richter of 2 years ago, where they proved that for a special kind of distal extensions, those given by skew products, some kind of skew products, they can lift the recurrence. I think it's only recurrence, not S recurrence. Yeah? I don't remember. Yes. In fact, you can make the computation for many examples. In fact, if you want to lift the recurrence in the classical distal system x plus alpha y plus x in the two torus, in fact, it's just a problem of solving a kind of integer equation. Yes. So there are no many ways to understand the skew products, in fact. But in any case, this is this is not achieved. So if you put here proximal and some skew extension, yes, of course, you will get at the end after transfinite recurrence, you can prove that such system that is obtained in this way with good equicontinuous extension, like those I mentioned before, the skew products, maybe you can get that the Kasnetson, let me see here, Kasnetson conjecture or question. But this just to come back to this conference. So what you can, this another way also to see a dynamical system. We know from, they say from a work with Bernard and Brian too, that we can create for any topological dynamical system, you can create these topological characteristic factors associated. So you have the topological Kronecker factor, the topological 2-nil factor, etc., and the inverse limits of all of that. So you also have these categories of factors associated to any topological dynamical system. Essentially, you have a weak mixing extension of the maximal distal factor, a distal extension of all this nil part. Yes. So you can try again to try to prove in a naive way that if you prove that the Bohr recurrence set is a recurrence set, but for all this family of systems, so the nil systems associated to a topological dynamical system, and after you can extend to the distal system, okay, this is the complicated part, yes, you can solve or can try to solve the conjecture if it is true. In any case, what we decide to do is first try to prove, in fact, that the Kasnetson conjecture is true for this family of systems. Yes? Was the most natural thing to do at that time. Yeah, here I want to emphasize another thing that is related maybe to what is discussing in this conjecture, in this conference. So what happens here, in fact? You have a topological dynamical system and you have this factor to the nil part, yes, associated to the system. So this is a long history I put in 4 lines, but essentially this is something that we call in topological dynamics the local entropy theory. But when you do local entropy theory, you can do also local zero entropy theory. And essentially, what you try to see, you take 2 points, and you try to see in which manner you transit from one point to the other. Yes. And when you transit to neighborhoods of one point to the other, you can try to see if you have some special recurrence or special sequence that allow you to go from one set to the other. In particular, you can ask if you have some IP sequences. Yes, this is very rough, but essentially, when you don't have such kind of IP sequences, and we call IP independence sets, you are an almost one-to-one extension of this system here. So that means that if your topological dynamical system is very close to the nil part, means that you don't have what we call IP independent sets, and it is exactly to transit between points over IP sets. Yes, and so when you transit between points through IP sets, you are quite far from the distal factor, from the nil factor, infinity nil factor. But when you don't have such transitions, you are very close to the nil part. And in this case, in fact, the Kasnetson conjecture could be true if we prove it is true also for the nil system. This is another way to write this. If you remember, we define, so this regionally proximal relation that produce those factors are coming from cubes. Those are the d-dimensional cubes. If 2 points are said to be paired with arbitrary long finite IP independent sets, if both points in any way appear as a cube. Yes, you can construct cubes with such points that are, you know, any combination of those produce a cube. So it's a very strong condition on the dynamical system. Okay, so this is a motivation just to try to prove, in fact, that for those systems here in green, the Kasnetson conjecture is true. So this is the first theorem that we prove with Brian and Bernard, is that you have a Bohr recurrence set then it is also a set of recurrence for all S nil systems. Yeah, so, and when you, in fact, since all those stuff here are inverse limits of S step nil system, so in fact, you have these for all those factors here. Yes, so, but maybe this is a good and bad news, but we prove in another paper with Bernard and Brian, in fact, that such factors, in most of the systems that we know collapse in the Kronecker factor, in fact. Yes, because when you have, and I will maybe show a consequence in a minute, is that when you have a nil system as a factor, that means that in the spectrum, you have continuous spectrum, yes, essentially. And this is essentially very difficult to achieve. Yes? So in many systems that we work with, in particular symbolic systems, so many people here work in symbolic systems with low complexity or zero entropy, they will never have those systems here. Yeah? But as has been shown by the theory, in fact, you need to prove many stuff for those systems to understand that some facts happens, yes, even if you don't know that they are all equal to the Kronecker factor. In particular, this kind of Kin-Chin counterexample by Vitali, Bernard, Braina, you know, they are true in most of this, are not true, the counterexamples, so the Kin-Chin type stuff is true because all those factors collapse. Okay, so how to prove this? There are essentially two proofs. One that is okay, it's a proof, but it's more disappointing in the sense that you don't really use the structure of the nil system. And another one that is where you can, but you need more hypotheses. We need to suppose that the group is connected, or even without hypothesis for the case S equal to 2. And the other one is more, I put delicate manner, but maybe it's not very delicate, but it's a proof where you really use the structure of the cubes and the structure of the nil manifold. Yes? So let's sketch just to give you a flavor of what happened in the first in this case. Essentially, you have a spectral property. This is the main point: is that when you suppose that your group is connected, or also in the case S equal 2, we wrote a complete paper proof for this case in an appendix, I think, in another paper. You have this property. When you project an L2 function over the Kronecker factor, and this is 0, then this kind of a spectral measure goes to 0. Yes, and this is the main, essentially the main tool is the fact that at the Kronecker factor you have very nice behavior, yes, of your operator. So what you will do is you will take your Bohr recurrence set, you will take an open set of positive measure because it's a minimal system. This the measure has full support. This is you can skip just to show you that after projecting and separating the indicator function in the projection and the other part, you have some bounds I will use. But by this property for large n, we know this is small. Yes, and after that, we use this another nice property of the Kronecker factor is kind of continuity of the projection on the L2 projection of on the Kronecker factor for translation. Yeah, this is continuous. So that means that if you are close to 0 here, because I will use 0, then these two maps, G and G translated by T are close. So now I use the recurrence, the Bohr recurrence. In the Kronecker factor, where is rotation by alpha, so I have an n such that these 2 points are close. I will have this inequality that I will put here to compute the measure of the recurrence. Yes, I went too fast, but essentially, when you write this, you can decompose in the projection to the Kronecker and the other part. This part is small. And this part you can divide and use Cauchy-Schwarz 2 times, and it's okay. So it's a really disappointing in the sense that you don't really use the structure. It's just a consequence of the fact that you are in the Kronecker factor and you have good properties of the Kronecker factor. Of course, you use the nil part is hidden here. Somewhere you need to use that this is nil. Yes, the very old results by Green, Han, and some other else. This old paper in the proceedings. To prove that you have this spectral property. When you go, if you want to prove this more in the the nil setting without hypothesis, I think extra hypothesis. In fact, you just project your system to an S-1 step nil manifold just by quotienting your group by the GS group in your series, yes, your nil series of groups. You get a factor, and what you will do is you will apply your inductive hypothesis for the S-1 still nil system, and you will try to lift this property to the S nil system. This is classical, so you will get an N in the S-1 nil system, and to lift, in fact, when you lift, since you have a big fiber in the factor, in the base you can come back very close to your open set, but in the lifting you have this GS group where you can move along the fiber. So in fact you will not come back to the open set, and this is the difficult part of the proof. Essentially, what you need to do is to solve, and this is what I try to put here. In fact, I don't have a lot of time, so I will not stop too much here, but you need to solve some kind of nil equation. You need to find some big N such that, and some HV in different groups, such that this is small. And this is the difficult part. You really solve an equation in the nil in the nil system. I can write you the easy proof of for one system, just to, I will say something that is false, but that you can generalize from this example. Yes. So for example, if you have this nil system, so this is an affine nil system, you can prove this is really a nil system. So you can see this system here doing X plus alpha, and you have fibers where you do the Y plus X. Yes. So when you iterate this map, it's something like here, and maybe, I don't know, something like here. So if you have a recurrence here, in fact, this point, if you consider some point here, you will not have a recurrence to an open set here. Maybe you will go here. Yes. So you need to control the movement here, and the way to do this, if you take a point close to the recurrence point in the base, you will get something like in the base, since this is an isometry, you can, any point you consider here will be very close to him after iteration. But here you need another control. Since all the points has this term, essentially you need to see if in a little neighborhood, multiplying by n in a little neighborhood, let's say, multiplying by n is surjective. Yes, if in this little neighborhood here, multiplying by some big N is surjective on the complete interval, you will be able to choose the correct Y such that you will come back to the same neighborhood. Maybe it's not completely clear, but what I want to say that is solving an equation. Yes, you really need to solve an equation to understand that you can lift a recurrence point for the base, that is a rotation, so a Bohr set, to the complete two nil manifold. Anyway, this equation in the general setting is something looks like this. Yes. Okay, this is for single recurrence. So what you can say for S multiple recurrence, first we need some notions that are classical for single nil recurrence. You need to define the concept of nil S Bohr zero sequence. So essentially you have a step nil system xt, a point, you have an open set, and the recurrence of this point to its neighborhood is called a nil S Bohr zero set. I think Bernard and Breiner coined this notion. I don't know, make a mistake. Yes, okay. So you will be nil S Bohr zero star if you intersect all nil S Bohr zero. And there's a very nice result by Wang, Chao, and Ye that proved that all the nil S Bohr zero sets, in fact, they contain S multiple recurrent types. Yes. So this is And this is very useful to prove the following, that is something that is true in the case of single recurrence, is that if you are a set of S recurrence for minimal S-step nil system, this is if and only if you are a nil S Bohr star set. Yes, and this is very useful for what we are going to prove. What this means, in fact, when you use some extra results not written here, this means that if you are to be L recurrent for minimal S-step nil system for any L bigger or equal to S is the same set, is the same thing as being nil S Bohr S recurrent. And it opened the question to know if you are S recurrent for an S nil system, are you also S recurrent for T nil system for T bigger than S? Yes, this is the main question that opened this kind of proposition. And this is the next two theorems. So this what we put in the paper with Bernard and Brian is that if you have an S recurrent set for affine S nil systems, then for any T, it is also an S recurrent set for affine T nil system. Affine meaning that you are giving in the torus, your map is given by this kind of transformation. I will not describe everything, but essentially it's multiplication by a good unipotent matrix plus an alpha. Yes. But in fact, this was generalized in some unpublished note with Wenbo-san. So in fact, the theorem is true in general, but this is unpublished. But so maybe I have to say that for the moment it's a speculation. No, someone said that before, but I think not. This was generalized after in some unpublished note that maybe will be published someday, that if you have a S recurrent set, then effectively you are S recurrent for S nil system. You are also recurrent for T nil system for T bigger than S. Yes. So the picture is the following. I will come back here. The picture is the following. If here you have the S step of the step of the nil system, and here you have the recurrence. So here are Bohr sets. So if you are recurrent for rotations, you are recurrent, you are 2, 3, 4, etc. recurrent. If you are two recurrent for two-step nil system, so you are recurrent 3, 4, S, etc. recurrent for the next steps. And in this direction is that if you start in the S time S here, if you are 3 recurrent for a 3-step nil system, then you are 3 recurrent for any step nil system with the T bigger than R. I put here in this way because of this discussion here and the unpublished notes. Yeah. But essentially you have this, and what is interesting is that you can construct counterexample for all the other arrows. So here is, so what I said before, you can have recurrence sets for S minus 1 recurrence set for an S nil system that is not an S recurrent set for an S nil system, for example, and all the other arrows. And of course, there are many examples that have been constructed ad hoc, but I want to emphasize this theorem by Wang, Song, and Ye that is very interesting to produce recurrent sets. So you have your minimal S-step nil system, and to produce the topological need factors I showed before, you have some relations, so some invariant relations that produce such factor. So you go, for example, you want to produce the S-step maximal, the S minus 1 or the G maximal nil factor for G lower than S. So you need to go to the RPG relation. If you take 2 points in the fiber of this factor, and you take an open set, a neighborhood of one point, such that it's not touching the other point, essentially, then the entrance time of this X0 to this neighborhood form an S minus 1 recurrent set. So each time you have a nil factor, in fact, and this is, you don't need to put here a step, in fact, each time you have a nil factor, you go to the fiber, you take 2 points, you make the entrance time of 1 point to the neighborhood, and you will create recurrent set. And by this proposition here, that you need to intersect all nil S-Bohr sets. In fact, you can prove that you can also, with this proposition, you can construct sets that are S-1 recurrent for S-step nil system, but that are not S recurrent. Yes, essentially, it's really kind of would you play with the word? It's two lines, in fact. Yes, it's a complicated language. So this is for the. This is what happened for the picture I showed before for this picture. So you can prove that all this is essentially is true. The castles of conjecture here and some extension, correct extensions of this set infinity set, and you have some, let's say, optimal result for S recurrent, yes? And counterexamples for all the other arrows. So what happened for a general group? I think I have, I don't know, 5 minutes, but I start before. So, okay. Do you want coffee? No, but it's very fast. It's so what happened to a general group? So those the other results are quite old now, not very promoted results. So the first time maybe that we show them. So what happened for general groups? So you have the same definition, and here I will be restricted to single recurrence. So you have the same definition and the same definition for classes of systems. So here, instead of taking n, you will take g and the action of d minus 1 over. So the recurrence g to the open set. So we were discussing with Felipe Hernandez, overall for Felipe Hernandez and Sebastián and myself, discussing about this problem for CD. So here I will just show two results that are in the process of being revised and corrected, etc. One is use cubes. I want to show this result. Maybe we don't know how strong is this result, but at least it's use cubes. And this is a very strange result. So you can, with Sebastián Donoso and Christopher Cabezas, we defined some years ago what we call the directional cubes that are defined naturally as the normal cubes for one transformation. So in this way, at each corner, you iterate all these commuting transformations in the natural way. You take the others, and those are cubes. Yes. So you will say, as always, that those cubes have the unique closing property. If 2 points that coincide in most of the coordinates, they will be the same in the last coordinate. Yes. And those cubes were created to emulate what Bernard did in his paper about magic extensions. So those cubes has this property, the property of being essentially product. So when you have the unique closing property. I'm really go very fast here, but essentially it's because you are the factor of a product system. Yes. And what you can prove for C2 actions is that if you are bored for a C2 action, then and you have the unique closing parametric property, then R also is a set of recurrence for such systems. Yes, so you can lift a little bit your C2 Bohr recurrence to this class of system. This is for C2 because of many technical problems. For D bigger than 2, in fact, you need to consider some strong unique completeness property. So that I will not show here. But just to say that this is a result that is related to cubes in some way. So when you are this morally like a nil, yes, because you have the unique completion property, but this is a CD action, so it's not a nil. So you can lift the CD recurrence, Bohr recurrence. And the last result I want to present, and this is also most of this was developed by Felipe in his master thesis, is that also for CD actions you can have kind of affine nil systems. I think there's a big discussion in some paper by Brian and Nikos about quasi-affine systems. So we consider this class, but essentially it's the same. You have commuting matrices and some other extra properties, and your CD action is given by that. So this is called quasi-affine CD nil yes, system. Nico said it was not him anyway. Huh? But anyway, we considered a affine case because we wanted to see if for a more large class without using cubes, if this is true. And in fact, you can prove also that if you have a CD Bohr recurrence set, then you can lift it to an S-step CD affine Nil system. Yes, so you also have this kind of, this is partial, but you have some extensions of the CD Bohr sets to some kind of nil, yes, in the CD category. So, but most of the stuff here is open. To prove this, and this is my last slide, this is just to show you that was necessary to create some concepts, in particular to create a special, to reduce your CD Bohr recurrence set to some special CD Bohr recurrence sets, verifying some approximation properties with respect of different irrational slopes that had appeared during the proof, in fact. But this can be done, and this is what we have. Thank you very much. No, this is to explore if we go to do some nil to the Atacama Desert, if you want. Very concretely, if we think, no, we didn't.
So the next talk resumes at 10:45. It's tea break now. Yeah, that is what I